In Module 7, we're going to go ahead and look at algebra involving trig ratios. So most of this module is going to involve using what are called trig identities. So when we talk about a trig identity, what we're talking about is an equation that is true for every number in the domain of the equation. So if we go ahead and look at our quotient identities and our reciprocal identities, which we've already talked about in terms of ratios, what that means is if I know tangent of theta is equal to sine of theta over cosine of theta, as long as theta is in the domain of our trig functions, then we know tangent is going to equal sine over cosine. So that's all it means for an identity, is that for whatever value I plug in for my variable, they'll be equal to whatever is on the other side. So as I said, we've already talked about tangent and cotangent quotient identities in another context. Cotangent is equal to cosine over sine. And our reciprocal identities. Typically, we've seen the second line of those reciprocal identities rewriting cosecant, secant, and cotangent, but we can also do it with sine, cosine, and tangent as well. We can think of them in terms of their reciprocal as well. So let's go ahead and look at an example. Given cosine of beta is 1/4 and tangent of beta is 4/9, we want to find secant of beta, cotangent of beta, sine of beta, and cosecant of beta. And we're only going to be using those quotient and reciprocal identities that we just talked about. So right off the bat, knowing cosine and tangent, I can find their reciprocals. So since cosine is 1/4, that tells me secant of beta is 4. And because tangent of 4/9, that tells me that cotangent is 9/4. So now in order to find sine and cosecant, we want to use one of our identities. And we're actually going to use the quotient identity for tangent. So we know that tangent of theta, tangent of beta is equal to sine of beta over cosine of beta. And we know tangent and cosine, so we can plug those in. So we have 4/9 is equal to sine of beta over 1/4. And in order to get sine of beta by itself, we multiply both sides by 1/4. So we get sine of beta equals, and when I do 1/4 times 4/9, the 4's will cancel, and we're left with sine of beta equals 1/9. And now that we know sine, we can find cosecant of beta, its reciprocal, and the reciprocal of 1/9 is 9. We also have Pythagorean identities. So these come from the unit circle, which we've seen before. So remember from the unit circle, any point on the unit circle, its angle theta is along the x-axis, its opposite side is y, the adjacent side is x, and our hypotenuse is r. So using the Pythagorean theorem on our right triangle, we get that the radius is equal to the square root of x squared plus y squared. So we have three Pythagorean identities. We have that sine squared of theta plus cosine squared of theta is 1, and this is the most important of our Pythagorean identities. We then have tangent of theta plus 1 equals secant squared of theta, and 1 plus cotangent of theta equals cosecant squared of theta. The reason why the first one is the most important is that the other two can be found just by manipulating that first trig identity. So let's go ahead and do a proof of these. So I'm going to start with the proof of sine squared theta plus cosine squared theta equals 1. And this is going to come from the Pythagorean theorem involving our unit circle. So on the unit circle, we know x squared plus y squared equals r squared. That's the right triangle we have on the unit circle. Because our goal is to have this equation equal to 1, we're going to divide everything by r squared. And when that happens, we get x over r squared plus y over r squared equals 1. Now x over r is just the ratio for cosine, So we have cosine of theta squared plus y over r is the ratio for sine. So sine of theta squared equals 1. A little rewriting, and we get that sine squared theta plus cosine squared theta equals 1. So the next ratio, next Pythagorean theorem identity we want to look at is tangent squared theta plus 1 equals secant squared theta. And we're going to start with our sine squared theta plus cosine squared theta equals 1 identity. So in the equation we're trying to get, this second term is 1. So we're going to divide everything by cosine squared of theta. So sine squared theta over cosine squared theta, we can write as sine of theta over cosine of theta squared. Then we get plus 1 equals, 1 over cosine is the same thing as secant, so we get secant of theta squared. Now using our quotient identity from the front, we get that tangent squared of theta plus 1 equals secant squared of theta. The last identity we want to prove is 1 plus cotangent squared theta equals cosecant squared theta. And again, we're going to start with sine squared theta plus cosine squared theta equals 1. Because our first term is 1, we're going to divide everything by sine squared theta. Now sine squared theta over sine squared theta is 1, plus I can write my second term as cosine theta over sine theta squared equals 1 over sine theta squared. So that'll give me 1 plus, my quotient identity tells me cosine over sine is cotangent, so we get cotangent squared of theta equals 1 over sine of theta is cosecant, so we get cosecant squared of theta. And we have proven our identity. And it's all based off that initial trig identity that sine squared of theta plus cosine squared of theta equals 1. That is the most important one to know. The other two you can get from manipulating just that first equation. So let's go ahead and do some examples involving all of the identities we talked about. So given sine of theta is 2/3, we want to find the values of our other 5 trig ratios. So let's start with the easiest to find. Because we're given sine, the easiest function to find would be cosecant, since it's the reciprocal. So we know cosecant of theta is going to equal 3/2. So now I want to find cosine, and what I can use is our Pythagorean trig identity. We're going to use that sine squared of theta plus cosine squared of theta equals 1. We know sine is 2/3, so we get 2/3 squared plus cosine squared of theta equals 1. When we square 2/3, we end up with 4/9. Subtract 4/9 from both sides, and we get cosine squared of theta equals 5/9. Take the square root, and we get that cosine of theta equals radical 5 over 3. And now that we have cosine of theta, we can find its reciprocal, secant of theta, which is 3 over radical 5. Now, with cosine of theta, the one thing I left out is because we took the square root, it would technically be plus or minus the square root of 5 over 3, but we're going to go ahead and assume that we're in quadrant 1 right now for our angle. We will later on talk about specific quadrants and how that affects our ratio, but for right now, we're going to assume that we're in quadrant 1, so everything is positive, but we don't have to worry about negative trig ratios. Now all that's left is find tangent and cotangent. So we're going to use our quotient ratio. Since we have sine and cosine, we know tangent of theta is sine of theta over cosine of theta. Sine is 2/3. Cosine is radical 5 over 3. So when I simplify this, tangent of theta is 2 over radical 5. And now I can find cotangent of theta, which is just the reciprocal of that, and we get radical 5 over 2. So I was able to find all other 5 trig ratios without creating a right triangle and using the Pythagorean theorem to find the hypotenuse. I was able to use just the trig identities. So our next example, we're given tangent of theta is radical 5 over 4. We want to find the exact values of sine and cosine. So what we're actually going to do here is, because I don't have enough information about sine and cosine to just say that sine is radical 5 and cosine is radical 4, we're going to use one of our Pythagorean identities that involves tangent. So we know that tangent squared of theta plus 1 equals secant squared of theta. So tangent we're given is radical 5 over 4 squared plus 1 equals secant squared of theta. Radical 5 over 4 squared is going to be 5 over 16 plus 1 equals secant squared theta. Five sixteenths plus 1 is going to give us 21 sixteenths. Take the square root of both sides and we get that secant of theta is radical 21 over 4. The reason why we use this is secant is the reciprocal of cosine. So I now know that cosine of theta is 4 over radical 21. And now that I have cosine, we can use another one. We can use either sine squared plus cosine squared equals 1, or we now have enough information to use our quotient ratio for tangent to solve for sine. And it doesn't matter which one you use, so I'll go ahead and show you both so that you have an example of each. So if I start with the quotient ratio, so tangent of theta is sine of theta over cosine of theta. We know we get radical 5 over 4 equals sine of theta over 4 over radical 21. Multiply both sides by 4 over radical 21. And we get that sine of theta equals radical 5 over radical 21. That's one way to find sine. Your second option is to use sine squared of theta plus cosine squared of theta equals 1, because we now know cosine. So we have sine squared theta plus 4 over radical 21 squared equals 1, which gives us sine squared of theta plus 16 over 21 equals 1. When we subtract 16 over 21 from both sides, we get sine squared theta equals 5 over 21. Take the square root of both sides, and we get sine of theta equals the square root of 5 over 21, which is the same thing as radical 5 over radical 21. We can distribute that square root to the numerator and denominator separately. But no matter which method you choose to use, both of them give you the same value for sine. So you had options. So next we're going to talk about simplifying rational expressions using our identities. And the goal when we're simplifying expressions is to always end up with sine and cosine, if possible. So when you're trying to simplify, you want to simplify so that you end up with sine and cosine when you're replacing your trig. So our first expression is sine of theta times secant of theta. So when we're simplifying that expression, we want to leave the sine of theta alone, and we want to rewrite secant of theta. Secant of theta is 1 over cosine of theta. That comes from the front of our notes. And then now I do sine of theta times 1 over cosine of theta. We get sine of theta over cosine of theta, which can be rewritten as tangent of theta. So tangent of theta is the simplified expression. It is equivalent to sine of theta times secant of theta. Our next example is 1 over sine of theta times cotangent of theta. So we're going to leave the sine of theta alone. So we have 1 over sine of theta times cotangent is cosine of theta over sine of theta. So we end up with 1 over, now when I do sine of theta times cosine of theta over sine of theta, the sines will cancel and we're left with 1 over cosine of theta, which 1 over cosine is the same thing as secant of theta. So secant of theta is equivalent to 1 over sine of theta times cotangent of theta. Last example, we want to simplify cotangent of x plus tangent of x. So we're going to rewrite both of them. So cotangent is cosine of theta over sine of theta, plus tangent, which is sine of theta over cosine of theta. Now, in order to add these fractions, they have to have common denominators, which they do not. So we need to multiply one or both of them by something that will get the same. Well, the only way for sine and cosine to be common denominators if sine of theta times cosine of theta is our denominator. So we're going to multiply the first fraction, the numerator and denominator, by cosine of theta. We'll multiply our second fraction, the top and bottom, by sine of theta. So when we do that, cosine times cosine gives us cosine squared of theta, plus sine times sine is sine squared of theta, all over sine theta cosine theta. And then from our Pythagorean identity, we know cosine squared plus sine squared is 1, so we end up with 1 over sine theta cosine theta, which can be rewritten as cosecant theta times secant of theta, since those are the reciprocals of, since 1 over sine is cosecant and 1 over cosine is secant. And that would be our final answer.